Okay. Okay, here we are. Good afternoon. Thank you very much to all the people who have decided to take part to this seminar, which is dedicated to, I think, a very interesting matter, which is assessment and monitoring of concrete structures. This seminar belongs to a series of seminars organized by Consiglio Nazionale degli Ingegneri together with CONCRETO Academy. The director, the scientific director of the CONCRETO Academy is Irene Matteini, we have here, and she will be one of the discussants of this interesting seminar. Our discussants will be today Irene Matteini, Luca Scappini, who is the member, one of the member of Consiglio Nazionale degli Ingegneri, which is the Italian Council of Engineers, Thomas Schumacher, who is professor of engineering at Portland State University in USA, and Professor Giulio Zani, who is assistant professor at Politecnico di Milano. Thank you to our discussant. Thank you very much for your collaboration and for your time. Just before leaving the microphone to Luca and Irene, I remind only a few things as usual. So I would like to say that okay, you will find Professor Schumacher's and Professor Zani's slides within the Consiglio Nazionale degli Ingegneri website, which is www.cni.it. I will remind you this in our chat, and I remind also that to all people who are listening to us will be awarded 2 crediti professionali for engineers, for Italian engineers, directly on my Eng personal page. Last but not least, I also would like to say that you are encouraged to write some questions to our discussant. You can pose your question in the chat, and I think that Irene will remind you this in a few minutes. So that's all. Thank you very much. I will pass the microphone to you, Irene and Luca. Thank you very much.
Thank you, Francesco. Irene, can I start just
yes,
for a couple of minutes, and then I give you the mic. Good afternoon, everyone. I would like to begin by bringing the greetings of the Italian National Council of Engineers and its President Perini, and by expressing our sincere thanks to the Pierluigi Nervi Foundation, promoter of the CONCRETO project, as well as to all the institutional and academic partners supporting these initiatives. The CNI, through its foundation, has joined CONCRETO with great conviction, as we fully share its mission to enhance and preserve the heritage of reinforced concrete structures, not only as a technical expression of structural engineer, but also as an essential part of our cultural identity and of the built landscape of the 20th century. CONCRETO stands out as an excellent example of European collaboration, combining education, research, and hands-on practice. It is a project that looks to the future, training young engineers and specialists who will be able to face the challenges of assessment, repair, and preservation of concrete structure through innovative and sustainable technique. As a National Council of Engineers, we strongly believe in the importance of such initiatives because continual professional education is the foundation of quality, competence, and safety in engineering practice. In this regard, the collaboration with the Pierluigi Nervi Foundation and the universities involved in a true model, it bridges advanced research with the professional experience and with the broader goal of protecting our built heritage. Let me conclude by once again thanking all the promoters and today's speakers. We are confident that CONCRETO will continue to grow and to foster a new culture of structural engineering, and one that is aware of historical and technical value of reinforced concrete and capable of innovating with knowledge, responsibility, and vision. Thank you, and I wish you all a very fruitful seminar. Irene, now it's your turn. Thank you very much for say hello to everyone.
Thank you, Luca, and thank you, Francesco and Fondazione, for this nice introduction. If I can be allowed to share the screen, I would just like to present you, to say a few words about the project and also the program of today. I would like to thank all the brave, all of you that on a Monday have decided to spend some time with us and to learn, to continue our learning journey with concrete rehabilitation and restoration. Benvenuti a tutti. This is the third seminar that we have organized with Fondazione Nazionale, a proud partner of the CONCRETO project and indeed the CONCRETO Academy. I am Irene Matteini. I am the scientific director of the program, which is led by the Pierluigi Nervi Foundation. Another really special thanks goes to our speakers, Thomas and Giulio, in particular Thomas, that woke up very early, that has joined us from Portland today to share some of his innovative research and really his work on assessment and monitoring. Before we get started with the program, I just wanted to share, to tell you what is CONCRETO Academy about and what is our mission. As Luca and Francesco have mentioned, it is a European project funded by Europe within the Erasmus Plus program that is led by the Pierluigi Nervi Foundation. It's truly conceived as a training program dedicated to professionals, students of architecture, engineering, and also craft workers that are primarily focusing on conservation and rehabilitation of concrete architecture. And really the special character of this project is that as really a very much the core value of it, it's the practical approach, or better said, the learning by doing principle. We are now entering our third year, and as you can see here, we have a very large consortium of partners, technical sponsors, and that have worked hard and supported to make this program very successful. We addresses the increasing demand for specialized skills and craftsmanship in the conservation and preservation of concrete structure through a series of different activities, starting from online lectures, technical seminars like this one today, through field session and practical and laboratory exercises where professionals get to work with actually the people that in the field are the one performing the work. So the ultimate goal of this, of CONCRETO, is to really bridge the gap between the academia world and the professional, the construction world. With that, I would like to really get to the topic of today. We are exploring the important role of conducting assessment, proper diagnostic, and indeed monitoring for our concrete structures, which should always be the first step that we take when we undertake any in the definition of any repair intervention. We have two presentations today that are attempting to tackle the importance of this topic. Our first speaker is Thomas Schumacher. Thomas has joined us from Portland. He's a professor at Portland State University, and I've had the pleasure to collaborate with Thomas in different projects in the past, and is one of the few people that can truly explain and talk about assessment and diagnostic in very simple terms, which always helps to get get the message across. Thomas is very much active in the American Concrete Institute organization, has been chair of the committee of 444, which is dedicated to structural health monitoring and instrumentation. With that, Thomas, I will leave you the stage. As always, thank you very much for being with us. It's always a pleasure to have you on board. Okay, now you can try to share, Thomas.
Thank you very much, Irene, for the kind introduction. I'm waiting to, here we go, be able to share my screen.
Okay.
If you can give me quick confirmation that everything is good. Okay,
yeah,
very good.
You can move on.
All right. So thank you again for having me today, giving me the opportunity to talk to you. As Irene said, I'm currently located in the US, but I grew up not too far from where you all are in Switzerland. I've been very interested in non-destructive testing, specific non-destructive evaluation, I should say, and I've always been interested in concrete structures throughout my apprenticeship in Switzerland and also through my studies. This is a bridge that's actually located in the United States. I always like to show this first. This is Luttrell Creek Falls. It was built in 1914 as a 3-span bridge, a very interesting arched bridge with a truss system. That's still operational today. Beautiful structure. It's located nearby a hike that we do with my family on a Sunday morning once in a while. This is on the beautiful scenic Columbia River Highway just outside of Portland here. But one of the structures that motivates me why we should really preserve the historic structures we have built. A quick outline. I want to talk a little bit about let me just get this. We go. I want to talk a little bit about non-destructive evaluation, what it is, how we in the United States at least have think of it. Then I have 2 case studies on non-destructive testing. Both have really a focus on imaging. And I want to make the case how useful imaging is and that it might not be as complicated to do and how much we can learn from it. I have 2 studies. One of them that will take the majority of the time, which is looking at a pre-stressed concrete bridge where no existing plans were available, but where an engineer needed to do a load rating, or we call it load rating, a structural evaluation. And imaging turned out to be extremely helpful in creating a digital cross-section of this bridge. Then I want to show a project that's always fun to share. I've gotten involved in the Scan Pyramids project a few years ago and been very active, and want to show some image fusion results there and how they were helpful in confirming a hidden corridor. I have a couple of structural health monitoring SHM case studies, but I don't want to spend too much time on those because I know our next speaker is going to talk more about it. But overall, I wanted to show the two approaches, NDT and SHM, and how they are really can be used together well to help with engineering and preservation of existing structures. And then some conclusions and outlook. And last, I always like to highlight on one slide sort of a new Master of Science focus area that we have created at Portland State University that's in this field. So how can NDE, non-destructive evaluation, help preserve existing structures? Actually, in a lot of ways, and we might not be doing it as much as we should. First of all, it will help us determine what is the structural condition. So it can provide us with inputs for finite element models, for example, and really help us in the decision making on how to proceed. It can also be helpful in monitoring after certain problems are seen by inspectors, and help us to make sure that safety is ensured until we have time to repair the structure. It can also be used to monitor after repair to make sure that that the repair actually works and as intended. For asset management, it can be used to help us basically accompany a structure throughout its life. I mean, this is not very often done, but it could help us along the way with maintenance and repair decisions. It really is helpful in extending the service life. Often we might have models, come up with models that might not be as accurate and might tell us that we need a replacement, but if we can actually install a monitoring system and use NDE, it might tell us that the stresses are not as high as we thought, as an example, and we can actually extend the service life quite a bit. And then this last part, digitalization, is of course an important term that we talk more and more about. So we want to create digital models. We want to have digital twins. So we want to have computer models that reflect as much as possible the actual structure. That will let us do tests, do evaluations, and help us in the decision making of maintenance and repair. So what is non-destructive evaluation? We like to think of it as sort of, there's two approaches underneath. One is non-destructive testing. This is where we take an instrument or a device, go to the structure, it's active, we control the stimulus, so we impart a pulse that could be a stress pulse, it could be an impact, it could be an electromagnetic wave, like in the case of radar. So we control the source and we look for the response of the structure due to it. So this will help us get a sense at the time, sort of a snapshot of the structure in terms of, depends what we want to find, the geometry of the structure. We could try to determine the condition of the structure and so on. So we do that once in a while. We deploy instruments, we take them back off. Here's an example of a ground penetrating radar device that a student applies on a concrete test specimen that we have in my laboratory. This is one of the graduate courses I teach. Structural health monitoring is more continuous long-term. We put sensors on the structure. It's passive, so we just let the structure tell us what's going on. We record the response. We could also use some active stimuli, like a test truck or something, or an impact, but typically it's passive, and that will really tell us the relative changes. So we don't know, we can't quite tell what the condition is at the time we start monitoring, but it will tell us when something changes. So both of these, NDT and SHM, we see sort of under this bigger term NDE. This is the terminology some of us have adapted in the US. Some of these terms are also used interchangeably. But underneath all of these is this idea of measurement, signal processing, analysis, visualization, evaluation. These are terms civil engineers, that's what I am, a civil engineer. Civil engineers are not always trained in, and that's what we're really trying to push for, to bring more of these skills into the curriculum. These are two, Irene mentioned, I'm active in the American Concrete Institute. I used to be the chair of the Structural Health Monitoring Committee. During my time, we produced this first report that you might find helpful. It talks about the different technologies used in structural health monitoring for concrete structures specifically. That's released. We are now working on a second report that focuses more on what to do with the data that's being produced by these technologies. I'm now chair of 228, which is non-destructive testing of concrete. You might be more familiar with this one. This is a pretty established report that shows the different techniques that can be used for non-destructive testing of concrete. We are currently working very actively on revising this. This report is over 20 years, over 10 years old, sorry. And so we're working on a complete revision of this report, just updating it with the latest information. So how do we combine them? Well, one idea might be just like when we go to the doctor, we get sort of a snapshot. The doctor might listen to our heart, might take our temperature, look at some other things, do a blood test, and that gives us an idea of the condition at that time. And then, so that sort of symbolizes the idea of non-destructive testing. If there is an issue or a problem, we might get a heart monitor or some other type of sensor that we can wear, And that is the idea of structural health monitoring. So from then on, we can keep track of what's happening and get real-time information. So the idea could be that we employ this in a very similar manner with structures. So if we look at this plot down here, on the y-axis, I have the health or the condition or the state of the structure. These are a little loose terms that we are still actually working on defining a little bit better. On the x-axis, we have time or age of the structure. So the green line is basically that health or condition. So as the structure ages, the health and the condition starts to decrease. And we might have some thresholds set where we want to pay attention to. We might be able to capture them or not. But the idea is, once in a while, we do visual inspections. So as an example, in the United States, for bridges that are mostly publicly owned, bridge inspections are mandated every 2 years. I know in Europe, it's every 4 or 5 years, depending on the country. But we can have visual inspections. If we have a visual inspection and realize that we might have crossed the threshold, we might employ some non-destructive testing to get a better idea. And if we have a concern, we might install a structural health monitoring system that will then let us more definitely tell when we should do a repair or rehabilitation, which is when we bring the condition back up to a good state. So this is how NDT and SHM can sort of work together to help us in this process of asset management and preservation. Let me get into my 2 case studies. And these first two case studies are basically related to non-destructive testing. The first one is this bridge. This is not a particularly glorious structure or anything, but it's actually a very important structure for the owner. This is the only access to a non-profit organization that helps people with addiction recover from their addictions. And they were faced with the problem that delivery people have said, we will no longer deliver to you across this bridge unless you show us that your structure is able to actually hold the weights of our trucks. So a structural firm was tasked with doing a structural evaluation. We call that load rating in the US, a load rating of this bridge. Because it was privately owned, it was built in the 1960s, there were no plans. So there were no drawings of any kind that were there. You can see this bridge, it has some green. This is what happens when you have a structure that's exposed to the environment and you are in the Pacific Northwest, which is where we live. There's a lot of rain in the fall, and so there's a little bit of moss buildup. The good thing is, historically, no de-icing salts have been used in the Pacific Northwest, where we do get some snow out here, but not much. But traditionally, no de-icing salts of any kind, de-icers have been used. So corrosion was not really expected to be a problem with this. And the visual inspection showed actually the underside of the bridge was very, very dense. There was no cracking on the bridge anywhere. There was just a little bit of this moss here. But again, the problem was we still didn't know what was inside. We really had no idea. It's simply supported, about 14.6 meters long. The idea was, or the guess was, that the cross sections look somewhat like this. They're prefabricated, pre-stressed concrete voided slabs. That's what the best guess that the engineer had. So it's basically, it has these big voids to save self-weight and make it lighter. But we didn't know. What we could do is measure the thickness, about 53 centimeters depth. And there were 3 of them side by side, and they were post-tensioned transversely to make a good shear connection. What was unknown, of course, was, are these voids really in there? How big are they? Could they be potentially filled with water over time? And then how many pre-stressing strands do we have at the bottom? That's very important to know. What's the cover? So any of these things were unknown. This is where the engineer called me and said, is there any way we could, that imaging might be able to help me figure out where all these elements are? Here's just another image on the side of the bridge. And here you can see a little bit underneath. The surface looked really good. There was, at one location, there was a little bit of a rusty spot, and that was associated with the post-tensioning that's going transverse. But the surface underneath was very clean, turned out to be very durable, very, very tough concrete, actually. We did some drilling. Very tough concrete, no cracking anywhere. So the first thing you can do as an option, if you do a load rating, is you can do a load rating in a simplified manner if you have no drawings. That is a very simplistic approach. It's highly conservative. And this is the table that the load rating manual in the state of Oregon, that's ODOT, the Oregon Department of Transportation, came up with. So the load rating engineer who tasked me with the imaging came up with this, and you can see a rating factor of 1 or above means the bridge is okay. It is able to safely carry the load. These are different types of trucks. They have little funky names, but these are different types of trucks, and you can see certain vehicles have rating factors below 1. The lowest one being emergency vehicle 3. That's basically a fire truck, a type of fire truck. So that would be bad news. If that facility has an issue, there's a fire or some other emergency, and the fire truck is unable to pass the bridge. So this was not acceptable. So we said, let's see what we can do with non-destructive testing. This is a plan view of the bridge. You can see the 3 slabs here. You can see the different measurements we took. So we have UEA, that stands for ultrasonic echo array. So we did some ultrasonic measurements. For imaging purposes, we have GPR, ground penetrating radar. We did some impacting to do some vibration testing. And we also used a cover meter to determine measure the cover thickness of the cover of the pre-stressing strands at the bottom. I was able to convince the engineer that I want to drill a hole in the middle vertically from the bottom to hopefully reach that middle void that we thought should be there, so I can measure that distance, and we can also determine if there's any water inside. We then used a little camera, a borescope attached to my cell phone to get in there and have a visual. So the images that I'm going to show you are really located a little bit closer to the support of slab number 2. So I was trying to recreate a cross-section of one of these slabs in great detail. I did take other GPR measurements. We did one over here too to determine the shear reinforcement and the cover of the shear reinforcement. But the images you'll see will be focused here. So here is where I did measurements both from the bottom of the bridge, but also from the top. What we wanted to make sure is that we have great confidence when we get these images, these cross sections. So we did some additional measurements. The vibration testing I mentioned, that will tell us something about the structural parameters. So now we're talking about the natural vibrations of the bridge. That will tell us something about the span length, mass, the stiffness, and mass. We were hoping that will tell us something also about whether these voids are water-filled or not, because the vibrations are a function of mass. That means if these voids are water-filled or air-filled, that should make a big difference. The cover meter I mentioned, that gives us a reliable depth of the pre-stressing strands. We also used a rebound hammer, a Schmidt hammer, to give us an idea of the quality of the concrete, the surface hardness. And then we drilled some holes. In one hole here to confirm the actual cover of the shear bar, and another hole, as I said, to drill into the void. So here are the instruments we used for imaging. This is a handheld GPR. It's very easy to deploy. Has a central pulse of 2.7 gigahertz. It sends electromagnetic or radar waves into the structure. The principle is shown here. So you have 2 antennas. One sends this signal a pulse into the structure, and then if you have something inside that reflects it, that comes back, and that can be received by the second antenna. Down here is a typical signal that is generated. We call it an A scan. And you can actually see the reflection from the bottom here of the thickness, in this case here, right here, this little pulse reflector. It takes a measurement every 2.5 millimeters as you roll this thing across the surface. Electromagnetic waves are really optimal at detecting metallic objects. So we're looking for dielectric differences between materials. You do get a decent reflection from an air surface as well, but it's really strongly reflects from steel. That can be a problem sometimes. If you have a very dense steel rebar mesh close to the surface, that can reflect all the energy back, and you can't really see very deep. But it's ideal to detect rebars or other metals. The second device we used is this ultrasonic echo array. This is a Pundit, and it has 24 transducers, but it's really 8 channels, 8 rows. So 3 of these always act as one channel. So it's really an 8-channel unit. You can see that now we have all these different combinations. So channel 1 sends a pulse, all the others are receiving that pulse. And then channel 2 sends a pulse, the rest of the channels are receiving. Channel 3 sends a pulse, and so on. So in one location, you basically get 28 measurements. And below, here's an example of one of such measurement. This is about 40 kilohertz. This is now based on an elastic stress wave. It's in the ultrasonic range, like 40 kilohertz is ultrasonic, so not in the audible range. The spatial resolution, so that's up to you. You can basically put this instrument down, take a measurement, move it to the next position, move it to the next position. We did, for this project, we used a 50 millimeter step, which gives you a spatial resolution of about 10 millimeters. Stress waves or ultrasonic waves here are really ideal at detecting air voids, boundaries. So this is what you can use to get the thickness of a member, or in our case, we were hoping to see the voids inside, if there are any. And so as you can tell, these instruments have different principles and are actually have their individual strengths. So based on that idea, once we can produce an image based on these measurements, and I'll show that on one of the next slides, the idea was, let's produce these images individually, and then maybe we can merge them together. And that's where image fusion comes in. Image fusion is used in the medical industries quite a bit. This is actually showing here the cross-section of a head. You can see the brain in here, an MRI, magnetic resonance imaging image, and here a PET image, positron emissivity tomography image. These two, it's the same idea. They give you different information about the brain. One of them gives you structure, the other one gives you more the functionality, blood flow, things like that. Now, if there's a way to merge these two via image fusion, we can get a complementary image, a single composite image that unites the different strengths, and that's actually easier to interpret by a medical expert. So the idea here is that we can reveal what's inside the structure with imaging. We can look at member geometry, material properties. In the process, we can learn about material properties. There's certain assumptions we have to make. We can visualize the reinforcement, and we can hopefully see voids and cracks. And image fusion will now take advantage of the fact that GPR and radar has different strengths and merge the two, and hopefully give us a better overall image of the interior. The way we do the imaging is called synthetic aperture focusing technique, or SAFT. And that's the technique that takes these these wiggly signals, these individual signals, and turns them into an actual cross section. I don't want to go too much into detail here, but the idea is that for one position, this is shown here, we divide up the cross section, so we have measurement direction and then depth here on the vertical axis. This is shown for just a simple two sensor setup. So if you send the pulse into the structure, it is reflected. So what you do with SAFT is for each of these little points, so you divide up this cross section into a grid, and then for each point on the grid, you draw this picture. You basically say, okay, I pretend that, in this case, I'm giving one example, I pretend that this is a reflector. I calculate the distance it takes to travel from the transmitting transducer to the point of interest and then back to the receiving one. I assume a wave velocity that gives me a time. And now for that signal that corresponds to this measurement position, I go into the signal and I read out the amplitude, which could be right here, for example, and I then go back and map that amplitude value to this point. Now I do that for all the different points on this in this domain. I do it for all the measurement positions and I add it all together. So if my point happens to be on a reflector, then at that point, hopefully in the signal, there will be an actual big amplitude that reflects that reflector. So we're basically focusing with this method, with the SAFT method, we're trying to get the reflectors to get the big amplitudes in the signals and have them focused on these reflectors. You might have be familiar with a B-scan. A B-scan is a little different. A B-scan simply lines up all these signals side by side. So this is a step further. This is really aiming to focus the energy to the reflectors. There's two unknowns that we have to determine. One is wave speed. As I said, we calculate distance divided by wave speed. The wave speed needs to be determined. That's a function of the material. And there's a time offset in there that we also have to guess so that the reflectors are eventually lining up in the correct position. So there's some calibration required. The cool thing is that once we have wave speed, that actually tells us a lot about the material. So if we have a very stiff concrete, in the case of ultrasound, if you have a very stiff concrete, it means the wave velocity will be very high. If we have a not so stiff, not so good concrete, low strength concrete, the wave velocity will be low. So there's some additional things we can learn. There's a lot of processing that goes into this, and there's really, I want to stress, there's no one way to create such an image. There's many things that can be done to enhance the image. So one image done by one person might look different than an image done by another person. But here's what we came up with in my research group, what these images look like. This is an example of a stepped concrete specimen. It's unreinforced. We take the measurements on top, and you can see properly calibrated. We can see actually these steps showing up in the image. So now we have a digital cross-section of this. You can also see something interesting happening on this step. You can see that we have this first reflection that we see as bright in the beginning and then dark in the second part. And for all other steps, it's just the dark band is before the bright one. The reason we have this is we put a piece of steel against this step here, and then air and the rest are basically just against air. So if I do a cross-section, vertical cross-section here, one through this part, one through this part, you can see that the received pulse is opposite. What that means is I can look at the reflector in the image and tell something about the type of reflector I have. I can tell you whether it's air or metal, or we could also tell whether it's air or water. The ultrasonic echo array image is down here. So the first one was radar. The second one is ultrasonic echo array. We didn't do the steel piece here, but you can see it's a little bit more noisy, but you can see the reflections of the back, again, dark reflectors. So this is the algorithms we came up with. We like to show it in this kind of way. So here are the results from the bridge. So here are the measurements taken from the bottom of the bridge. So basically measuring up. You can see from the radar image, we have a very strong reflectors here. These are the pre-stressing strands. There's a bunch of additional bands that you see here. They are really multiple reflections that are not real. They're just caused because you have a very dense first layer of bars. You send that electromagnetic wave in, and that wave now bounces back and forth. And that causes these, what we call multiples, to occur. We did also see a teeny little dark reflector here, which we were thinking might be associated with the void. The ultrasonic echo array image very clearly showed these voids. That was very nice to see. So indeed, this is a voided slab, it turns out. Between the voids, we could also see the top of the slab, which was very helpful for making sure we assumed the right wave velocity. Now we can fuse them together. I didn't spend any time explaining how the fusion works, but fusion could be as simple as just adding the two pictures together, taking the average, if you will. Sometimes I do that even in PowerPoint. I just put the two on top and then play with the transparency of one image to get a first idea. We use a little more complicated way, but we're basically merging these images via image fusion. And in essence, it could be as simple as just taking the average of two images. Images are just in MATLAB language. If you use MATLAB, it's just two matrices, and you take the average of the matrices. Again, we use a little bit more complicated method, but this is what the fused image looks like. And you can see we have a very clear indication of the pre-stressing strands, but also the voids are shown very clearly. Further confirmation that's nice is if these reflectors actually line up, they're in the same position, then we also know that for both cases we assumed the right wave velocities. You can see here the wave velocity for the radar wave and the wave velocity for the shear wave. This is the ultrasonic array we use as a shear wave device. So about 2.62 meters per millisecond. That's a fairly strong stiff concrete, which tells us it's a dense concrete, which is likely a strong concrete. These are the measurements from the top. We have the radar showing up some mild reinforcing bars on top. There's no pre-stressing, but some simple mild bars. And we can also see the voids here. Because the layer of steel is not as dense, at the bottom it's about 50 millimeters, the spacing of the strands, and they're 13 millimeter diameter strands, pre-stressing strands. So that's very dense. It's hard to penetrate radar waves to penetrate through that layer. Here it's much more open, so we can actually see the voids. The ultrasonic array image, the same thing again. We can see the voids, and we can also see this very nice back wall here, which tells us that the velocities, the assumptions are correct. We fuse them together, we get this. And then we said, okay, why not fuse the bottom and the top together? So we have this image here from the bottom, we have this image from the top, we fuse them together, and now we basically have a cross section that we can work with. It's still a little bit noisy, but we have all the information in here. We see the voids very clearly, we see the reinforcing on top, we see the pre-stressing strands at the bottom, and we know that they are correct because the reflectors of each match, and we also could see the back wall. So this is now a confirmed image that we can use. We can go in and actually read out dimensions. I will revisit this. Here's just some results from the vibration testing. I used a simple cell phone based measurement here. That's Fifox. It's an app that you can use to measure the vibrations, the acceleration response. We just jumped on the bridge, measured the response. We identified some modes, some flexural modes of the bridge, some torsional modes. We did build a finite element model, a slab model, and came up with these, basically played with the material properties. and we also tried to fill the voids with water and fill the voids with air. And the best results we got to match these peaks in the model were these, and it told us, the model told us, we need the voids are most likely air filled. Rebound number, I want to make it clear here that I'm not suggesting that you should take rebound measurements and convert them to strength, but what we wanted to see here is, per the manual of bridge evaluation, we were only technically, without any measurements, you can, and if there's no drawings available, based on the age, you're allowed to use about 21 megapascals for concrete strength. We did these measurements, we distributed them across the bottom, we converted them with the manufacturer curve to strength. We found some research that helps us adjust for carbonation because that skews the measurements. We adjusted that. And then the engineer asked me, can I use about 34.5 megapascals for my load rating? And I said, that's, based on what we see, that's about over 3 standard deviations away from this estimated curve based on the rebound hammer measurements. And we decided that we are comfortable using that value for the load rating. There was really no indication that just looking visually by the drilling combined with these measurements that should be a problem. The rebar detector, here we used this Profoscope to get about a mean cover of about 36 millimeters for the pre-stressing strands at the bottom. This is showing a photo from inside the duct. I'm looking at the formwork actually. So we drilled from the bottom into that middle void, pushed the camera up, and you can see the formwork material. No water came out. Second indication, confirmation, these voids are not water filled, they're dry. Showed this fibrous board. The measurement from the bottom of the slab to the bottom of the void was about 157 millimeters. So now what we can do, we can take this, we can go in and we can determine all these measurements. So we know we can determine the size of the void. That helps us determine the self-weight of the structure exactly, which is an important part in the structural evaluation. We can measure, based on the reflectors, we can measure the cover. In the image, we got about 38 millimeters. The rebar detector said 36, so we're very close there. The distance from the bottom to the middle void in the image told us it's about 155 millimeters. We measured 157, so we are within a couple of millimeters here. So this has turned out to be very useful. This is what we anticipated. This is what we had, and it turns out they were very close, except for the cover here of the rebar, of the pre-stressing strands. That was a little bit different. But now we knew exactly what to work with. The engineer redid the load rating. This is what I showed you earlier with the simplified method. Using this exact digital cross-section, we now had rating factors that were basically above 1, even for this emergency vehicle number 3, which means this bridge is safely able to carry all the different truck types that are legal in Oregon, including emergency vehicles. And that was, of course, a big relief for the owner of the bridge. So very useful. Case study number 2. So this is about the Scan Pyramids mission. I want to show you how imaging was very useful in this case. This is the Great Pyramid in Giza. And this is the north face. And you can see this here is what we call the chevron. This is what basically right below these blocks, these big chevron blocks, was the original entrance to the pyramids that leads to the different chambers. There was a suspicion that behind these blocks might be a hidden corridor. That was determined based on measurements done with muon tomography. Muons are particles that exist in the universe, fly around. They're not harmful, but it turns out if you can set up detectors and detect them, so you can basically the analogy would be X-raying the pyramids, but here you do it with a passive source with these muons. These measurements were done in the 2015-2017 range. The scientists from Japan said there might be a big void that is currently not known in the pyramids. This is basically a cross-section through the Great Pyramid. You see some existing structures that are known, the Queen's Chamber, the King's Chamber, the Grand Gallery, and so on. But they said we can see a big void up here that's basically deep inside the pyramids. They also said behind the chevron, it appears there might also be something. So we were pointed to this area. We went there, we applied radar, ultrasound with the same tools that I just introduced. We also used electrical resistivity tomography, which gives you an indication of the electrical resistance of the ground, the underground. These three techniques were applied to these chevron blocks. You can get a sense of the size of these blocks here. This is over 2 meters wide. So this is the application of radar applied in the vertical direction. So that was sort of pulled up by a cart. Here's one radargram showing a strong reflector at about 90 centimeters depth. This is ultrasound, again, same device that I showed you, applied in the horizontal direction here in this case. You can see at a depth of about 90 centimeters, again, a very strong reflector showed up. Electrical resistivity tomography, these are the electrodes glued on or attached to. You inject the current, you measure resistivities at the other electrodes. You can then reconstruct the conduct or the resistivity map. This is actually a vertical cross section. This is the chevron blocks here. You can see there's a high resistivity volume behind, basically behind the blocks here. And that's one of the things we couldn't tell with radar or GPR. You know
Thomas,
that you have a, yep.
Excuse me, sorry for interrupting you. I would like to strongly engage people who are listening to you to write questions in the chat. It's very simple. Incoraggiamo chi ci sta ascoltando veramente a scrivere, a porre le domande al relatore. Approfittiamone della presenza, diciamo, di un esperto, di un collega per porre delle questioni, dei problemi, dei quesiti che avete. Come si dice in inglese, don't be shy, non c'è problema, scrivete quello che volete e porremo la domanda al relatore. Sorry, thank you very much.
That sounds good. And I know I think I have about 5 or so minutes left. I'm trying to stay within that so we have time for questions and of course the second speaker. Okay, so we could tell that there's a reflector, but what you can't tell is that is behind that. Is it just a 1 centimeter air gap? Is it a 1 meter air gap, or is there an even bigger void behind? Electrical resistivity tomography showed that there might be a much bigger void behind it. Imaging and image fusion then helped us reveal that. So I'm showing here a view of the chevron again. There's a horizontal cross-section that I'm showing here on this side. This unites all the 3 measurements. In this case, we fused the images from GPR, ultrasonic, and electrical resistivity tomography together. We could see very strong reflectors here in 2 locations, around 90 and a little bit more like 80 centimeters. And then behind it, there's this big high resistivity volume, high resistivity indicating that there might be air. On this side, you see the reflector. This is based on a GPR measurement. So this was, we were basically able to show that in this slice here, this vertical cross, this horizontal cross section, there's the blocks that we can see, blocks 3 and 4, and behind it might be a big air volume. And then that's what was revealed in March 23. They were able to push a teeny little camera from below into this, and that's what they found. So we found this cross section, about a 9-meter long tunnel. That was a big reveal. Since then, researchers have created photochromatic reconstructions here of the tunnel, giving you a better sense of what it looks like. Yeah, I want to mention that this is a big effort. I work with the Technical University Munich on this project. The Cairo University is really the technical lead on this. And everything, of course, is under the scrutiny of the Ministry of the Antiquities of Egypt. But we are a big international team working on this, and this is ongoing. I do have a few more things here, but I don't want to get too long. A couple of SHM, structural health monitoring case studies that I worked on that are also reinforced concrete. Here is one where we embedded ultrasonic transducers into a column. This is a full-scale bridge column. This was basically loaded horizontally in a cyclic fashion. So this was a seismic experiment, not dynamically, but it was pushed back and forth. I had both ultrasound and acoustic emission. So these are this is basically an active and a passive way. Acoustic emission will record cracking and damage that's occurring internally. The ultrasonic transducers here were used to I basically had an active pulse in the middle, and then the bottom and the top one, they were recording the response. So here is just the very first phase when we started loading the column. Up here is the displacement and the axial load in the column shown. Acoustic emission, you start to hear these cracking noises. That's what shows up as you're loading the column, as you vary the displacement. And then you can see here the upper and the lower ultrasonic transducers embedded in the concrete. The top one, throughout the loading process, had a constant amplitude for the signals, and the bottom one started to actually pick up some changes when we varied the lateral displacement. So this path down here started to get cracked, and we could actually see that. And so actively, you can see when stuff is happening, when you have cracking, when it's occurring in real time. With the active ultrasound, you can detect teeny little changes over time. So here we wanted to show that these two approaches, they can also be done with the same equipment, can be very useful to assess a concrete structure over its lifetime. And here there was some emphasis on an earthquake. So what happens during an earthquake, what happens after an earthquake. This is a real-life study where ultrasonic monitoring, passive ultrasonic monitoring, so acoustic emission monitoring, was used to monitor the pre-stressing wire breaks, an old system in Germany that had issues with corrosion. They instrumented the whole bridge. There are strain gauges, displacement sensors, and you can see the green sensors are acoustic emission sensors, so they're based on ultrasound. And this basically helped extend the service life of the bridge. This is now being replaced, this bridge, but this was a really great case study to show how structural health monitoring can be used. Problem is found, the bridge is instrumented, and now it can be kept safe. I think maximum weights of trucks was reduced to make sure there's no issues, but a way to keep the structure safe for the public while you figure out a solution. These are some sample data that were done with trucks. I don't think they detected active wire breaks, but these systems are now very popular in Germany, and we're actually working on a guideline, again, monitoring of pre-stressing wire breaks. So to wrap up, NDE, so both non-destructive testing and health monitoring, I think is a great support tool that is helpful in the engineering and preservation of existing structures. With NDT, specifically with imaging, we can really get an idea of the structural condition as it is, a snapshot. And with SHM, we can then monitor changes over time. We can get really accurate digital cross-sections. If we can do all the measurements that are useful, it's not that difficult to do, but extremely helpful. And using multiple methods at the same time is always recommended for cross-validation of measurements and reducing uncertainty. This is our program that we have now offer, our Master of Science focus area that's really built around engineering and preservation of existing structures. You may take there's some more information behind this code, or you're more than welcome to write to me if you have any questions. So with this, I want to thank you and see if there's any questions. I think I stayed within the time. So there's a couple of references. You have these slides. Please feel free to email me directly. We're happy to share the code that we developed in my group to do both imaging and image fusion. It already has found some application, I think, and we keep extending and improving it. We're also doing training if required. So if you have an interest, we're happy to share that. So thank you.
Thank you, Thomas. Always pretty inspiring. We have some question. I think we have some of the audience asking about the case study 1, so the little bridge. One of the easy question is how long did it take to complete the assessment of the bridge, and why was the preference to use non-destructive testing besides, you know, doing some sample or static load test?
Mm-hmm. So the budget was very limited in this case. So this, I should say, this was a real opportunity for me. There was basically, I don't think they had much of a budget at all for NDT in this case. And so the engineer, I had known the engineer for a long time. And so he had hired, basically all he had done, they had a budget to do some radar testing to determine where the shear reinforcement is, and maybe to get an idea where the pre-stressing strands are. But anything else that was, you know, they didn't want to do more. And so I did certainly, a lot of this was done on my part just because I was really interested to see just how much I could do. So I wouldn't say it's necessarily representative in terms of what we charged them. You know, in terms of time, I would say taking the data is maybe you can, for this bridge, all the different NDT information I showed, including GPR, ultrasound, vibration testing, cover meter, drilling, I think you could do that in a half a day. So I would say 4 or 5 hours is for this bridge. Of course, it's a small bridge and we focused on one beam. It can be, if you're efficient, maybe you have 2 people out there can help each other. I think you can do that in a half a day. I would maybe a little bit more, but that's doable, I think. We were not quite that organized as researchers, so we went out there several times, but that's that. And then the analysis piece, doing the imaging, piecing it all together, that takes a few days, of course, to do all that.
Okay.
If you know what you're doing. For us, it was really learning on the spot. You know, we had a lot to learn on the spot, but it was great because it gave us all this practical experience.
On that, I want to follow. I want to ask you a follow-up question on image fusing, because it is a very powerful method. Because often we know that, you know, we have to combine different data set, we have to use different testing method, and one of the challenging and hard work is when we go back to the office and try to make sense of all the data that we collected. Based on your experience, and you know, we appreciate that you appear to be generous enough to share the code with the system that you have developed. How doable is to do it in terms of timing and effort when working on larger structures with limited budget and time, you think?
Well, I don't know. It all depends, right? How I have the luxury as an academic to spend more time than I could where I like you know, in the consulting world, of course. This was ideal if you, so the fusion part, it doesn't always make sense to do it. So I don't want to give the impression that that's always the solution to do image fusion. this was quite ideal. In some cases, maybe it makes sense to just keep the images side by side. But when you're, in this case, it was very helpful because merging them, showing that the reflectors align and all that, gave us all this extra confirmation that the material properties and, you know, it just completes the picture. But of course, it gets more complicated when you have bigger images and you know, and more of them. I think if you have more cross sections on the same structure, it might get easier because you have to figure it out maybe for one, and then you can just multiply that, right? But it can certainly take considerable effort to, you know, especially if you have long cross sections. Again, this was a very compact, nice cross section that was easy to see. If you have very long cross sections, it can get more difficult to sort of keep just keep an overview of what you're looking at. So yeah, I don't know that I can give you a very definite answer. Yeah.
No, that's okay. That's okay. And in terms of like preferring the application of non-destructive techniques versus the destructive test, there is a question that is asking if you can tell us a little bit more about, you know, the cost and the economic convenience. And I would add, you know, the less intrusive approach, especially when working on historic structure, or preferring non-destructive versus destructive testing.
So in this case, in this bridge, we were not allowed to do any coring. I would have loved to have a concrete core so we can correlate that with the rebound, even just one, right? To correlate that with the rebound hammer, because you should not, I want to make it clear, it is not recommended. It's actually not permitted in most countries to take rebound hammer measurements and convert them to strength and use that strength. So unless you do also coring and you correlate that with coring. We were just not allowed to do that. The best we could do is, I was happy to get that, to be able to drill that hole. And that gave us also a sense of how strong that concrete is. You can think of NDT as a multiplier, right? If you can do some cores and you can correlate your non-destructive measurements, you can then calibrate your NDT. And now NDT you can apply much more widespread, I think, and much quicker. You can't do too many cores, obviously, you know, so that you're limited in how much cores you can take out of a structure. But NDT you can apply as much as you want, right? It doesn't cause any harm to the structure. So you can think of NDT as a multiplier. So you can calibrate your NDT measurements based on a few cores. And so then you can do cover more widespread. You can cover your structure with NDT. I think that's how I like to think of NDT.
Nice. Can you, when working with foundation depth, when we're trying to understand the interface between, you know, the reinforced concrete foundation structure and soil, can some of this technique be applied? Which one would you say work best for this application?
So depending on the depth, I would. So if you want to know concrete depth of, that's a very common problem. Yes. I would say I would try with ultrasound. You can get ultrasound with the devices we use. You should be able to get a depth up to over 1 meter, I would say, probably even more. And I think I haven't done any foundations, although it looks like I might do some in the future. But you should be able to see the difference between concrete and soil. That is not uncommon. I think that's done. It's not the same as against air, that's for sure. But especially if you have sometimes we have this layer of low strength concrete, right, that we put on the soil before you cast the structural concrete. That might give, because there's a lot of air content there, that might help you also give you a sense. Sometimes that shows up too. But you should get a clear indication, a reflection with ultrasound. Radar might also work, but depending on the thickness, you might have to go with such a low frequency that, you know, the resolution just drops quite a bit. And radar is always, if you have a lot of reinforcement, it's hard to see through a dense mesh of reinforcement. And so I would probably try with ultrasound, because you can go quite deep. But you have to be able to calibrate it. You have to get a good idea of what the wave velocity is, which you can obviously do to get a sense of, yeah.
Makes sense, makes sense. There is another question from a colleague in the UK that primarily is working on masonry. What are some of the techniques that you can apply also to masonry from the ones that you commonly use with concrete structures, that you would say?
Yeah, I don't have much experience with masonry, I have to say. I mean, are we talking concrete? I mean, you know, cement-based masonry, or is it clay? Or, I mean, that will make a difference too. But masonry is very challenging, I would say, because it's not as homogeneous as concrete. Right? You have all these layers, and it should still work with. I mean, it depends what you want to find. If you want to locate anchors, I mean, you've done this, right, in Chicago. If you want to locate anchors, then I would say then use GPR, because that should work pretty well to locate metals in masonry. Yeah. If you want to know thickness, it might also work with radar. But again, if you have different layers, it gets a little bit tricky, I would say. Technically, ultrasound should work, but it gets pretty complicated, I think.
Yeah, I think I have to say that another way that we use GPR on masonry is when we found areas that were voided, and then you do your GPR survey, and then you grout everything, and then you do your GPR survey again to make sure that you actually did fill the voids and did proper grouting. So there are some techniques that can be translated, but definitely it's a very different materials. So I would say yes, I agree that not everything it's compatible to use with masonry.
Yeah, again, I don't have too much. You have probably more experience with masonry than I do.
I think I just wanna ask you a final question in terms of, or like a reflection in terms of, like, you have been working with NDT for a while now. And you have seen the introduction of AI in the last years. How you see that some of the improvements have been assisting the data processing and also the application of NDT, and where you see it in 10 years?
Oh, wow. Yeah. I want to say I'm a fairly
You didn't expect that.
I'm a fairly slow adapter of AI, I have to say. But I would say I'm trying to be very pragmatic about it. I see it very useful as an assistant. So if let's say, that's how I want to use it, and how we're starting to explore some of the machine learning and AI techniques to say, okay, let's generate this image. Can AI do some labeling? So we have done what we call image segmentation. It could help with that, where it basically picks out reflectors and helps you identify regions that you might want to take a closer look at. What I don't like in what I see sometimes, what I don't like is this completely automated like analysis of things, right? Where it turns into a black box exercise that just tells you, here's the result. I don't like that. But as an assistant that might say, hey, you might want to check out this, or you might want to do this, I see that could be very useful. And then you still are the expert, you still have control. I mean, there's many ways it can be used. If you have lots of measurements, you can start to you do need lots of measurements to do that, basically, where you can train a data set to help you identify things. So that's always the challenge. And if you have to know where the limits are, right? Understand the limits of the data sets that you use to train your algorithms. So I'm sure we will see lots of cool things to come in the future, especially also on the visualization side. So I just would be careful. Yeah, you have to know the limitations of the methods that are used.
Indeed, indeed.
I know this is a very general answer. I don't know that.
No, let's hope that we still get to go in the field and actually do this assessment, that we really don't rely just on robot and drones, because that's part of, you know, the interesting aspect of doing this, of getting involved with this type of work. I think the pyramid project is, you know, if that doesn't get you convinced enough that doing diagnostic and assessment is extremely exciting, I don't know if you can find many other structures that can do the trick. But Thomas, thank you very much. This was very exciting. Thomas has shared the contact, so please feel free to reach out. He's a very nice person, so he's always open to collaborate. You are welcome, Thomas, to stay on, but now we are going to move to the next presentation. We have Giulio Zani, Assistant Professor of Structural Engineers at the Department of Civil and Environmental Engineering at the Politecnico of Milan, and more importantly, Giulio is a key expert in the CONCRETO Academy consortium that really has played an important role in the training program. Giulio, buon pomeriggio. Welcome. We are now going to tackle even a more urgent question, that is, you know, taking care and maintaining our infrastructure, that it's indeed not only an Italian problem, but it's a worldwide international problem. The stage is yours, Giulio. Whenever you are ready, you can get started. Thank you.
Thank you, Irene, for the introduction, and good afternoon, everybody. First of all, I would like to thank the Fondazione and the CONCRETO Academy for having me here. This is a nice occasion to share with you some of the information I gathered over the years in working on several infrastructure distributed across the Italian territory. So first of all, I would like to start with some context, because it's very important to understand the place in which we're working and the reasons why we need to design some monitoring systems and also develop some diagnostic investigations which helps our understanding which is the safety level of structures. And over the past decade, we observed in Italy several collapses of infrastructure and of bridges. So what you see in this slide is a timeline of recent bridge collapses which took place in Italy. You see a series of yellow dots highlighting the frequency of these collapses, which of course appears to be quite challenging and quite worrying also for the general public. For sure, one of the first collapses that raised global awareness and also pushed people into understanding more about existing infrastructure, and also pushed the politics and also the managers in carefully observing structures over time, is the collapse of the unknown overpass. So this is a collapse which was related, according to the assessment which was carried out during the trial, by corrosion-related problems. So in the presence of a severe cracking, you see this picture here inside the Gerber saddle, and the lack of robustness led to the failure of the whole deck. And during investigations, some investigations were carried out also here at the Politecnico di Milano by Professor Di Prisco and my general research group that we have here in Lecco, was related also to some corrosion phenomena. So the presence of contaminated waters which attacked the reinforcement, leading to a loss of cross-section and finally to a collapse. But just 2 years after this event, which took place in Lombardy, we all know what happened in Genova. So in Genova, we had the failure of a very important structure, so the Viadotto Polcevera, which caused 43 fatalities. So this was very impactful, and it was a confirmation of a global picture, which is a worrying global picture, which stresses out the need to carefully observe, maintain, and preserve and strengthen existing reinforced concrete structures or existing infrastructures in general. Something I would like to point out is that everybody observed that the majority of recent structural failure took place in reinforced concrete and pre-stressed concrete bridges. And this is a very important point because some people thought that these failures, which were mainly related to the material itself and not to the lack of maintenance or the natural aging of this infrastructure. What we need to observe and to stress out is that more than 50%, way more than 50% of the Italian bridges is actually made of reinforced concrete and pre-stressed concrete. And this is because concrete still remains today a very cheap material, which can promote also the development of infrastructures in different countries, also in developing regions, because of its possibility to be shaped into different sizes, different shapes, and also to create large infrastructure which can support, for instance, traffic loads, or which can be used for energy production. So a larger share, about 80%, this is generally complicated to carefully estimate these numbers, but about 80% of the Italian bridge stock was built before the 1950s and 1960s. And this is also a very interesting observation because we can realize that most of the structure have surpassed the expected service life, which was conceived at the time of their design. So at this point, one might ask, is it just an Italian problem? And the answer is no. Some years ago, I had the chance also to attend to a presentation by Philippe, who is a chief engineer at the Federal Highway Administration in the United States. And the FHWA has in charge about 600,000 highway bridges over more than 4 million miles of roads in the United States. And what surprised me at that time is that over about a little more than 30 years, between 1980 and 2012, they recorded more than 1,000 bridge failures. And according to a rating which was carried out in 2001, nearly 30% of bridges in the United States are classified as substandard because functionally obsolete or structurally deficient. So this is a global problem, and if we take a look to the causes of these 1,000 collapses, we see that in most of the cases, the causes are naturally related, so floods and scours, so hydraulic related phenomena, while degradation counts only 7%. But this is not a small number because while the time passes, also the possibility to assist to a degradation or increase degradation and also a failure which is triggered by degradation becomes larger and larger. So according to another study, again from the United States, in which the researchers studied samples of 500 bridges of various types failed in 1989-2000, so a little more than 10 years, they observed that about 50% of total bridge failures were associated to structures which were made of steel and not of concrete, as we observed for the Italian case. In this particular sample of bridges, only 10% of failures were associated to concrete-based structure. And this is something that imposes a reflection also on the reaction that in Italy we are having about these failures which took place over time, because in most of the cases, the post-failure actions consisted in the substitution of original reinforced concrete or pre-stressed concrete structures with steel structures. So we see the case of the unknown overpass, which is substituted now with a structure made of weathering steel, and the other cases like the Fossano and the Genova Bridge, in which the main deck is now made of steel. So this is a key point, and I wanted to stress this out because I have the feeling, also discussing with a lot of managers and a lot of engineers, that at some point let's say we had the misconception of reinforced concrete as a dangerous material and steel as a more reliable material, but this is not fully true, because we just observed that in different countries, based on different technological traditions and also construction traditions, we might assist to several failures also on steel structures. So the material is not the main point, because this is a problem which is not material related, but it's related to the lack of maintenance and the lack of observation. The Viadotto Polcevera was a very important bridge because it was a pioneer application of pre-stressed concrete technology. So as most of you surely know, pre-stressed concrete technology was imagined and was patented at the end of the 19th century, but only after Second World War it was possible to build significant full-scale structures because of the new materials, the new high-strength steels which were available after World War II. But the choice, even though this bridge was very, very clearly welcomed as an innovation also on local newspapers, was to demolish the remaining parts of this bridge. And this was also contested by many people in Italy, because this was also an example of cultural heritage. So this was a testimony of Italian engineering and also the advancement in design, and this is lost forever. This was a pioneer application, but since the 1970s, significant creep effects and also corrosion at some point of the structures were observed. And we always need to keep in mind the role of the level of knowledge at the time of construction and also the technology at the time of construction, because this was, as I mentioned, an application which was very brave, let's say, because it was one of the first of its kind, due to the presence of these pre-stressed concrete stays, which consisted on a set of different cables. So we had primary cables and secondary cables made of high-strength steels. And this is a picture actually from the construction site in which you see a phase of construction of the stays. So this is still under investigation, but also in this case, one candidate of the cause of collapse of this bridge is corrosion. So we know now that corrosion is a big issue in reinforced concrete. We have several initiation parameters like carbonation, the presence of chlorides, acid rains, and sulfates, but this is not enough. So in general, if you have a structure, for instance, this bridge, which is subjected to carbonation and the presence of chlorides, which might be related to airborne salinity or also the de-icing salts, this leads to the passivation of the reinforcement. But in order to develop some corrosion products, you always need also moisture and oxygen. And this finally leads to the creation of corrosion products, which have a volume which can increase of about 7 times with respect of the original material, inducing some self-stresses and finally the loss of the concrete cover. Moisture is one of the ingredients that, in my experience, I always observed in all the structures which were very corroded and severely corroded. So it's a very important ingredient. If we go back to one paper by Riccardo Morandi, we can understand that since 1979, so about 10 years after the design of this bridge, he also realized that the bridge was subjected to a slow deterioration because of the effect of movable loads, because of the environmental action. And he also realized the role of the advancement of technique and technology of pre-stressed concrete, because he was a pioneer in the application, and he understood that these had some limits in terms of understanding of the complex phenomena which are behind this kind of structure. So his suggestion back in '79 was to carry out a careful observation of the structure over time and carry out in a quick and proper way some remedial works, so some interventions. He also stressed out the role of the aggressiveness of the atmosphere. We are very close, of course, to the seaside, and also stressed out that he thought about 2 possible options. So one option was the structure made of pre-stressed concrete, and the other one was a structure made of steel. And at the point, or at the time of the design, he realized that maintenance cost would be much higher in presence of a steel solution. if we think about heritage structures, so we move from Genova to another places in Italy, we generally think about historical infrastructure. And this is a case study I had the chance to work on some years ago. This is a middle-age bridge, so something that people generally consider heritage. So heritage, because this is some testimony of the past, and in particular, this bridge is very significant because it was built when Italy did not exist at all, and this was actually on the border between two different states. So this was also the location of some battles, and this stress out the need to carry out some historical studies, and the importance, the strategic importance to carry out some historical studies to understand which is the evolution of the time of the structure, and also to obtain some very interesting information for the assessment. For instance, you see on the right the evolution, the time evolution of this bridge from the 14th century to the 21st century. And what is interesting is that we were actually able to reconstruct this original configuration through a fresco, which was documented, a battle which took place very close to this bridge in the Middle Age. This was important because this allowed us to understand which was the original load to which the bridge was subjected, and also gain some information for the structural assessment. This is a case in which we carried out a series of diagnostic investigations, including investigation on the soil beneath the foundations, and a series of non-destructive and partially destructive tests, including then also a load test on the biggest span of the bridge to understand which was the maximum service load which could be introduced to the structure. But if we think about heritage, we have also different examples which are not generally so recognized as Middle Age structures. The first one is the Ponte del Risorgimento. This is a design by Pierluigi Nervi. I had to put this because I'm responsible of the Laboratorio Nervi here in Lecco, and I couldn't avoid including also something about Pierluigi Nervi, but this is very interesting because it's a bridge made of reinforced concrete. You see that the age of this bridge is of about 60 years. So also this structure has surpassed the service life, but what we observe also, even from this picture, is that we don't see very significant signs of deterioration because of the careful detailing and the design which was carried out by Nervi over time. And another example in which we have a strong heritage meaning is the Ponte sul Basento by Sergio Musmeci. This is a bridge in which you see the potential of concrete when used, of course, to create complex shapes. And this is also a very interesting case study because this is actually ongoing some restoration intervention and some retrofitting interventions which will restore the original image of this bridge. So, given the context, I would like to stress out that, as you have seen, in 2016 and 2018, we had two significant failures which raised the awareness of at the national level on this problem. Nowadays, we have some guidelines which guide the managers and also engineers in assessing the safety of existing bridges. But back in 2018, the national guidelines were not effective. And Regione Lombardia launched a research project together with the Politecnico di Milano by signing an agreement on the definition of criteria and guidelines for the maintenance and the management of road infrastructure. So we have a very large region, a very large population, about 1/6 of the whole Italian population, and the estimated number of strategic bridges is of more than 10,000. So you see that we involved inside this project a group of more than 20 professors, postdocs, and PhD students across 4 different departments. And one of the objectives was to develop some management and monitoring guidelines and also select a set of demo cases which could be used as benchmarks for the preparation of these guidelines. And today I will be discussing and I will be introducing you one of these case studies on which I was particularly involved. This is a multicellular reinforced concrete bridge in northern Italy. This is close to the municipality of Brescia, and this was built in the 1950s. The global length is not very significant, so it's about 43 meters over 3 spans. The central span is supported by 2 piers, and then we have 2 cantilever spans of about 10 meters span. The variable depth is between 1.4 and 2.8 meters, and we also have the pile foundation. So the question we asked ourselves was, how can we monitor this bridge on a limited budget, finding also useful information for the management of the maintenance of this structure. You see that this is a structure which is not in a very bad shape. So we have some local problems of corrosion, but most of these corrosion problems are associated to the areas which are close to the joints. So the presence of some water, of course, water leakage at the joints. But these are the points which are the least stressed of the structure, because we are on a free end of a cantilever span. In addressing this methodology, we had to design a step-based methodology, which could be then extended to several bridges across the region. So first of all, we had an archival research and documentation, which is then followed by inspection, condition survey, then design and installation of a monitoring system, which is a static monitoring system, in this case designed for the management, as I mentioned, of maintenance. And this was then validated and followed by load testing, observation, and finally the numerical modeling to construct a twin, let's say a digital twin of the bridge. In assessing the bridges which were considered in this project, we analyzed about 290 bridges in Lombardy. And for all of them, we tried to collect as much as possible the documentation, the original documentation. You see that this is not a simple task, because in only, let's say, 48 cases, we had both design reports and technical drawings out of the 289. So this means that this is something quite common. So we saw before also with the previous speaker, a presentation in which no technical documents were available. And so this stresses the role of inspection and also the role of diagnostic. We carried out a series of investigation on this bridge, and I forgot to mention we had a limited budget, because the overall budget for this was of about 40,000 euros for both the diagnostic investigation and the development of the monitoring system that I will be explaining in the following. You see that in most of the cases, corrosion phenomena are localized in the regions in which we have the highest humidity, so the lack of a drainage system or the presence of leaking joints. In terms of the set of inspection activities that we carried out at first a laser scanner survey, which was then followed by a photogrammetric survey, ambient vibration tests to assess the dynamic properties of the structure, followed by some concrete coring. Also in this case, the number was very limited, but we were able to carry out ultrasonic pulse velocity tests, carbonation tests, and uniaxial compression tests. Then we performed some carbon tests on the piers, some radar scans. So this is again a GPR on both the piers and the deck, and then a series of sonic and ultrasonic pulse velocity tests on both, again, the deck and the piers. We also developed some rebound hammer test, a specific location, in particular close to the concrete coring, and then distributed throughout the whole structure. And then where possible, we also measured the exposed rebars to understand the differences between the original design and the final constructed and the as-built situation. This is something very important because, as you can see, thanks to the three-dimensional laser scanner, we had a very good geometry of the structure. And with orthophotogrammetric imaging, we could also trace the existing cracking pattern. This was very important because this also supported us in defining the correct location of the devices and the transducers that I will be discussing the following. But one key point that we observed in this case is that in the original drawing, which we obtained from the manager of the structure, we could count 1, 2, 3, 4, 5, 6, 7 girders in the cross section of the deck. While just by observing this structure from the bottom and then by interpreting the 3D laser scanner, we realized that the number of girders in the as-built situation is just 6. And I always try to point out this because this is very important. After this initial assessment, we also obtained some calculation reports, for instance, for the passage of heavy trucks, which happened over the time on this bridge. And we realized that many technicians actually use this information of the original design to assess the safety of this bridge with respect to the passage of a large truck. And this is pretty dangerous because you can see from these that you have an overestimation of the capacity because you are considering one girder more than what is present in the as-built situation. And sometimes just a careful observation, just counting these technical holes that we have, we can estimate the number of cells, and so we can estimate the number of girders and find that there is some kind of difference between the original and the as-built design. In the assessment phase, we had the possibility to carry out some mechanical characterization tests on concrete. And in particular, as you can see here, we carried out some coring, over which we measure the ultrasonic pulse velocity test, and we also have a measure of carbonation. So carbonation front is pretty deep, 60 millimeters, 35 millimeters, depending on the porosity of different materials. But what is interesting is that besides the homogeneity, which was measured by means of ultrasonic and sonic, in this case, transparency tests, we were able to obtain some information from the coring. So after 70 years, we have these two strengths. So the pier is much more porous and a less quality concrete than the deck. But we were able to go back to the time of construction. So just after 28 days after casting, thanks to some formulation that you find, for instance, inside the model code 2020. And you see that we obtain some strengths which are in line with the strengths of materials in the 1950s. This is something which is extracted from a database which was built by the Politecnico di Torino, thanks to the collection of several certificates issued by university labs. And so for different decades, we have an idea of the range of strength which was currently used, was actually used. This is something which is similar to what also the previous speaker presented you, and we had the chance to carry out some GPR scans on the bridge, and these allowed us to confirm the thickness at some point, so the thickness of the structural parts, and also to identify the position of the rebars, which were also reported inside the original designs. But we understood that, of course, some differences were present, and we needed to understand whether, at least for the layout of the reinforcement, the information that we had in the original design was sufficiently correct. So we had several scans on the deck, understanding the number of layers of reinforcement and somehow the global thickness of the technical layers that we have on the deck. And this is a section, so the section G3 on the lateral girder, in which we see all the stirrups, the spacing of the stirrups, and sometimes also additional reinforcement as this diagonal reinforcement that we have here in this reproduction of the original drawings. The dynamic characterization allows us to obtain the frequency of the mold shapes and to reconstruct the dynamic characteristics also over different configuration and different environmental conditions. So one test was carried out on February and one on June, finding just some modest differences between the two. The next step was the design of the monitoring system. So again, here we were on a limited budget, so we needed to optimize the number of instruments and the transducers that we needed to install. So you see an overview. We had some tilt meters to measure rotation. We have deformometers to measure displacements and also crack opening. And then we have some surface temperature sensors, one weather station, one hydrometer to measure the level of the river, and also a digital camera. We were lucky enough in this case of having a bridge which has a cantilever part. So this means that we could fix the base, let's say, of the transducer on the abutment, and then the head of the transducer to the intrados of the deck. And these allowed us to measure, of course, the vertical displacement at the end of the deck, which is something that it's not always feasible on a bridge structure. The installation took place over a couple working days, thanks to some climbers which installed the devices over the structure. This is an example of one reading. It's about 10 days. Then I will show you that we observed the bridge for quite a larger time. But you see that if we observe the vertical displacements, so the 1 to the 6 at the end of the deck, we have a behavior which is characterized by a slow fluctuation, which is mostly associated to the thermal loads, so the presence of the solar radiation, plus a series of peaks. And this is due to the fact that even though these devices were conceived and are designed for static monitoring, we acquired the information and we recorded the information at a sampling frequency of about 40 Hertz, collecting also some information associated to the passage of moving loads, so the passage of vehicles. So at this point, we decided to run a moving average to extract the behavior associated to thermal loads, and by operating a difference between these two measures, we obtained the displacement associated to the variable loads alone. And you can see the days with the least traffic, so Saturday and Sundays, we have smaller displacements because we don't have large trucks. And we also validated these measurements since this was made with a static monitoring transducer with a laser sensor, which is able to obtain information at a higher sampling frequency in a more precise way. From these, we observed that the actual measurements that we obtained also from the static transducer is pretty comparable to the one that we had with the laser. In some cases, we lost some part of the information because of friction, internal friction effects inside the transducer, but we were able to assess the ordinary traffic induces in this particular bridge displacements, which can be occasionally larger than 2 millimeters per about 2 millimeters is the threshold of these vertical displacements. A key point in assessing this bridge was also validating the monitoring system by means of a load test. So we had the occasion to install the monitoring system because the scheduled passage of a heavy goods vehicle. This was a massive truck, so you see 34 axles, 76 meters long, 380 tons of global weight. And we could impose two loading conditions, one stressing mostly the central span, leading to a positive curvature, and one stressing mostly the two overhanging spans, the cantilever spans at the two sides of the central one, leading to a negative curvature of the deck. This is the measurement which was provided again by our monitoring system, reading displacement D1 to D6 at the end of the deck. And what is interesting to observe is that these heavy goods vehicles induce vertical displacements which are generally smaller than those observed under ordinary traffic conditions. This is something very important because in most of the cases there is the common idea that exceptional load is always less safe than ordinary traffic, but in some cases it is not the case because of course we need to consider how distributed this load is and how slow, and the passage which was in a central position and not in eccentric one. Over the time we had this chance to observe the structure, understanding that both temperature fluctuation and also vertical displacements tend to have let's say, an effect which is related to the seasonal change, with no particular change between 2 subsequent years. However, we also measured with some transducer the integral crack opening displacements in these cracked areas, assessing that over time we have a limited but pretty clear increase of crack opening. So it means that this is something that should be worked on and should be understood with higher precision. You see that thanks to the tilt mirrors that we installed, we were able also to record the rotation of the deck, both flexural and also torsional rotations. A pretty nice way to understand whether a measurement is just environmentally related or is also related to the effect of moving loads or the effect of different, let's say, degradation phenomena is to plot the displacement values, for instance, with respect of temperature. And this is the overall measurements of 2 years. So this is 2 years of measurements. This is a big data, what they call big data. So it's pretty complicated to work on this data. But what is clear is that here we have a correlation between temperature and displacement. So in some cases, the correlation is pretty clear. So we can assess that this is mostly related to environmental effects. While in some cases, and this is the case of cracks or transducers monitoring crack openings, we see that we don't have a clear linear correlation. So this means that this is a phenomenon which is not strictly related to temperature variations. Something very important was the model updating. So this was the final phase of this research in which we were able to calibrate a numerical model on ambient vibration tests. Here you see the comparison between one mode shape on one side of the bridge. The comparison is between the red curve, which is the numerical one, and the black and light blue ones, which are associated to the experimental measurements, and also the cross MAC matrix, which highlights how the numerical model gets closer to the real measurements. You see that we were able to calibrate the numerical model on these measurements, and this is something that it's generally done, but also to validate then this model on the load test, which we performed on this heavy goods vehicle. And we realized that the model calibrated on ambient vibration test fails to reproduce the displacement observed under static load. And this is something that has to do with existing structures in which we might have some friction effects at the supports, some also nonlinear behavior at the joints. This is a very complicated joints with some bitumen mastic, a buried slab, and then a set, let's say, of layers, technical layers above this joint as well. So this is something important because only after a further calibration of the static model, we were able to obtain a good agreement between the numerical results and also the experimental measure that we carried out during the passage of these trucks. I will now proceed with some conclusion because the time is almost over. So first of all, what I've shown you is a monitoring of a 70-year-old reinforced concrete bridge, which is still operating on a heavy traffic network. Of course, the diagnostic campaign revealed that you might find significant discrepancies between the design documents and the SBL situation, and this confirms the need for on-site validation in safety assessment. Tests also highlighted some degradation risks, such as carbonation-induced corrosion, and confirmed material properties which are typical of 1950s reinforced concrete construction. It was very important in this case study to understand the existing cracking pattern and to record and detect the existing cracking pattern to target sensor placements. This also allowed to obtain a cheaper, let's say, version of the monitoring system, locating the transducers at needed location, but highlighted also the need for continued monitoring. In this case, the static monitoring system, even though it was limited in terms of number of transducers, captured displacement and rotation, including the effects of moving loads, which was something not expected at the very beginning. And also the load test shown that exceptional loads are not always more critical than ordinary traffic condition. We also found some discrepancies, so please be aware that optimizing and tuning the numerical model on ambient vibration test is sometimes not enough, because it's always important also to have a static load test to understand whether the modeling is effective. And the knowledge that we produced thanks to this activity is now being used in maintenance and retrofitting works. So it was given to the designers, which are now addressing the interventions which were planned on this structure. I reported here again one sentence from the previous paper by Morandi, in which he understood that sooner or later, maybe in a few years, it will be necessary to resort to a treatment and to cover everything up with elastomery of a very high chemical resistance. So this is something that we generally do, but something important is that we should postpone as much as possible the need of introducing additional materials and restore the original structure or the original capacity. To do this, I just wanted to point out some experiences I had in working also with ANAS, which is the largest manager of roads in Italy. And in many cases, what I observed is that some very small defects, as the absence of a piping system or the failure of the drainage system, might lead to very severe damages over time. So this is the case of this external beam, in which the absence of a pipe led to the failure also of some tendons made of high-strength steel. And this is the case of another bridge, which is in a pretty good shape, but the leakage of water led to the corrosion of this support. And you can imagine which is the cost associated to the substitution of a support of this kind. And in doing this, it is important to always remember what we call the rule of 5. So if the cost of preventive maintenance is 1 and this is postponed, then you might have to introduce minor repair with a cost of about 5 times the original cost of preventive maintenance. If you avoid doing the minor repair, major repair might lead to a 25 times expense, and full replacements even to 125 times. Meaning that the growth, let's say, of the economic burden of defects is exponential and it's not linear. So the first and most effective response to structural deterioration is regular maintenance and also continuous observation, which allow the detection of damage and prevent costly interventions over time. And the last message I leave you here is that at the same time, it's essential to continue with the development of innovative materials, because this will be the basis for the retrofitting of existing structures, but also for the design of new durable infrastructure. And I reported here a couple examples. One is the Butterfly Bridge in Japan by Akio Kasuga, which uses very high performance fiber reinforced concrete to create thin walled elements characterized by significant durability. And the other one on the right is the Pont de la République by Ricciotti in France, in which we have a very nice, let's say, also appearance of a bridge because of the high strength of this material, which allowed for the design of very thin sections characterized by a great architectural expression as well. And with this, I thank you. And I also leave you here my email address. So if you have any curiosity, please feel free to reach out. Thank you.
Thank you, Giulio, for this hopeful presentation. We are now close to the finish line. There is just a couple of questions, and then we're not going to delay any further. We will let you go out, have an aperitivo and dinner. But the first question is, by comparing results of both dynamic analysis and load test, were you able to do some consideration on dynamic and studying young modulus of existing concrete?
Okay, so in this case, we actually extracted some properties on the elastic modulus of concrete by means of the ultrasonic pulse velocity test, mostly. Not directly from the structure, because we also had the problem of the presence of a pre-existing cracking So the presence of pre-existing cracking could not be explicitly introduced inside our model because we have, in this case, an homogeneous three-dimensional model. So we modified somehow the elastic modulus to capture the behavior, but we tried as much as possible to keep it consistent with what came directly from the diagnostic campaign. So to address this information, in some cases, we also tried to reduce the elastic modulus at specific locations, like it's generally done by 50% in the cracked regions, but this wasn't sufficient to obtain a good match between the numerical model and the experimental observation. So this is something which was strictly related to the boundary conditions.
Okay, thank you. And Giulio, as a closing reflection, you know, based on your experience with structural monitoring project and your interaction with departments of transportation, how do they generally have responded over the years to the idea of implementing monitoring system? Do you see growing interest, awareness, and willingness to invest in adopting valuable tools for managing existing structure? Again, you said it earlier that, you know, not all the monitoring system require really large budget, but what is your take in your experience?
Yes, I have several ideas about this, no? Because first of all, they understood quite well that it's important to observe all this structure, which is a big success, you know, of all these activities that on a national scale were carried out. So it's very important that all structures are now observed. And there is also a very strong interest in monitoring systems and also in low-cost ones, because there is the feeling that it's impossible, of course, to install very complex and costly monitoring system throughout different structures. There are some developments in which some typology-based monitoring systems could be imagined and could be installed. And also I connect to the artificial intelligence that you said before, but in some cases it's also possible to extend observations carried out on some archetypes, let's say, of structure to other structure which are present on a national scale. So this is something that it's done. But of course, there is a strong awareness, but I also think that what is very important is to keep in mind that each structure has its own monitoring system. So not every system can be adopted over different structural types. So we should keep in mind that all options should be always considered, let's say.
Very much agreed. I think we, in closing today, thank you very much, Giulio and Thomas. We've seen really a diverse array of techniques from the more sophisticated one to really simple techniques. And, you know, the key message that we would like to come across today is, yes, conducting proper assessment is very important, but also it is indeed very important to, when approaching a new project, before going out there and using all the techniques, the fanciest one is first to understand what are the types of information, what are your research questions, the answer that you try to find. This should really drive your approach and not really let the machine, the testing equipment really drive it. Because sometimes, you know, you don't need all the fanciest thing out there to get you the answer that you need. And this really reconnects to the fact that, you know, you don't always need a big budget to conduct assessment. And these, as professionals, it's also your duty to push an owner to really do it before really, you know, asking you to design and details or, you know, determine specification on how to intervene. With that, I would like you to, on behalf of CONCRETO Academy and Fondazione, thank you for joining us. We hope you enjoyed it. Mark your calendar, because our next appointment is December 12th. Right before the holidays. Make sure to follow us on LinkedIn and subscribe to stay updated on all the different seminars and activities that we conduct. Thank you again, Thomas and Giulio and Luca and Francesco. I leave the stage to you. Buona serata a tutti e grazie.
Thanks, Irene. I would like to say that we are still receiving some messages, as Irene, you can read. Even some teachers of our academy are sending the compliments and congratulations to our speakers. I would like to say thank you to the 331 people who are still online. And I would like to say thank you to Giulio, Thomas, and Irene for the competence, for the time, consideration on behalf of Consiglio Nazionale degli Ingegneri. As Irene said, at the very beginning, if I'm not wrong, of December, we shall have another seminar. I think it will be very, very interesting, like this one. I don't know if Luca would like to say something.
Well, I just want to thanks Irene, Giulio, and obviously Thomas, who woke up early this morning. So I'm very happy. Thank you all. And Francesca, I'm always happy when we have a seminar in English. It's not so easy in Italy to do something like that, but it's very successful. So I'm double happy today. Okay.
Engineers are always very surprising, as you know. So thank you very much. See you in the next seminar, which will be on Friday.
Bye.
Thank you.
Ciao, thank you.
Bye-bye.
Bye, everybody.
Bye, everybody.
Thank you.
Thank you.